Welcome Physics 142 students. What I'd like to do is start with a review of the situation where we have two point sources of waves producing interference at a common point P, and then, since we've been talking primarily about sound waves in this regard, we'd like to extend this to a situation where we have light waves interfering and show some of the really striking results that we get in that case. So first of all, what we've got here, and I believe I showed this in class, is waves coming from two sources where the waves are initially in phase, but they travel a different distance to reach the common point P, where there's an observer. And so that path difference, which is the extra distance traveled from source 2 to get to point P, that's what we refer to as delta R. And if that path difference is an integer multiple of a wavelength, then we find constructive interference. The waves add up constructively at point P. If that path difference is a half integer multiple of the wavelength, then we see delta R equals 1/2 lambda, 3/2 lambda, or so on. That leads to destructive interference. In other words, a minimum in the intensity for the waves at point P. The m in both these equations is an integer which begins at 0 and has all possible non-negative values. So that's the interference from 2-point sources. And just a reminder, in order for this kind of interference to happen, we need sources that are coherent, which means that whatever phase relationship they begin with, that stays the same all throughout. So we talked about two different ways to achieve this. With sound, we can have two speakers that are driven by the same amplifier. With light, we achieve this by having two slits in a screen that are in front of a single light source. So now let's turn our attention to a classic experiment using light that's referred to as Young's double slit experiment. Thomas Young was a brilliant man. He was trained as a physician, but was also an amateur Egyptologist. He made real contributions to the theory of color vision and to optics in general. But what he's primarily known for in physics was his facility with this experiment that took a single light source, which of course, while we might use a laser today, Young probably used light from the sun or some other secondary light source, and that light came in on an opaque screen with two tiny slits, indicated here by S1 and S2. And light coming through these two slits acted like two different sources. The blue lines show the path that the light would travel to go from the two slits to reach a common point P on a viewing screen. The viewing screen is a distance L away from the slits. And so what is truly amazing about this experiment is that what we see on the screen is not just some smeared out distribution of light that maybe gets a little fainter towards the top and the bottom of the screen. Rather, what we see are alternating bands of bright color, bright light, separated from each other by regions of relatively no light or minimum light intensity. And here, the red rectangles indicate locations on the screen where we see bright streaks. And these streaks are called fringes, bright fringes. So what Young's experiment did, and we'll analyze it here in a moment, but in the history of physics, what it did was establish conclusively that light, at least in this experiment, behaved as if it were a wave. There had been a great controversy going back to the time of Newton and one of his compatriots, Huygens, in the 16 and 1700s, as to whether light was really a stream of particles or whether it was more properly regarded as a series of waves. Huygens believed in the wave theory. Newton, however, with his greater prestige, his theory had to do with light being a stream of particles, and by and large Newton's theory was more popular at the time. Huygens and his successors believed that light actually had a wave-like character, but it wasn't until Young's experiment in 1801 that this wave nature of light was conclusively demonstrated, because it showed the presence of constructive and destructive interference that can only really be understood if light behaves like a wave. So let's analyze this experiment and figure out the conditions for constructive interference, which is where the bright fringes are, and then destructive interference, where it's dark in between the bright fringes. So with a suitable analysis of these two paths, R1 and R2, we can make a very good approximation, assuming that the distance between the slits is small compared to the distance to the screen. And in that approximation, what we see is that the extra distance that the light has to travel coming from source 2 is this distance here labeled with the double arrow. And the two paths, S1P and S2P, are very nearly parallel to one another if the point P is very far away. So in that case, we form a right triangle, what is very close to a right triangle anyway, that goes from S1 to S2 and over to the point at the end of the tip of the arrow, with the dotted line as one of the legs. And so this is shown in the cutaway view, the smaller view over here, as the bottom leg of the right triangle. And if the hypotenuse is given by the slit separation d, then that extra distance is d sine theta. And that's a good approximation because usually the slits are very close together in a physical situation that we would construct. So that's the path difference. R2 minus R1 is d times the sine of the angle theta. And we can show again with some simple geometry that the angle theta opposite that side is the same as the angle theta that tells us where the point P is located. See, because the angle that point P makes, the leg that goes from the center of the slits out to point P and the horizontal, that angle is theta as well. And so d sine theta for constructive interference is simply an integer multiple of the wavelength, just like we showed a few minutes ago. And for destructive interference, d sine theta has to be a half integer multiple of the wavelength. And what we see here are the different m values that the fringes correspond to. M equals 0 would give us a path difference of 0. That's because at the center of the screen, light that comes from the two sources has to travel the same distance. That naturally leads to constructive interference. But then if we move up a little bit, we can see the minimum in the curve here, right in between the two adjacent regions of constructive interference. That would be where d sine theta would be 1/2 wavelength, and so on and so forth. So the m equals 0, 1, 2, 3, and 4, and then also the negative values for those regions below the center line where we see the bright fringes. Those are the m values that you would plug into the equation for constructive interference. Destructive interference, again, just means there's no light, and that happens in the ideal case exactly in between the two adjacent bright fringes. So this problem, this kind of a problem can be done when we know, for example, the slit separation, and we know the distance to the screen, and we want to find out where on the screen a particular maximum or minimum in light intensity occurs. Well, that naturally leads us into a consideration of how do we find that distance y. And really it's just a matter of geometry. If we want to find the separation between fringes. Here the diagram illustrates that y is the separation between the central fringe and the m equals 1, 2, 3, the third fringe on the top half of the viewing screen. So y, of course, rigorously is just equal to L times the tangent of theta. Right? That's an easy calculation to do. The tan of theta is y over L. And now the small angle approximation is helpful in simplifying this, because if L is much larger than y, in other words, if the interference fringes that we're looking for are fairly close to the center of the screen, and those distances are small compared to L, then the tangent of theta is approximately equal to theta. And so y would simply be, although it's rigorously L tan theta, that would just make it L theta. Then we can take the expression for the location of the interference fringes that are the bright fringes for constructive interference, and again, if theta is small, then sine theta is also approximately theta. And both sine and tangent are approximately theta because for small angles, the cosine is very nearly 1. So those two numbers are about the same. This transforms the equation for constructive interference to d theta equals m lambda. And if we put these two equations together, we can solve for y. Solve for theta in the second equation, that gives m lambda over d. Plug that into the first equation, and we get the distance to the mth fringe. Of course, the 0th fringe is distance 0 because it's exactly at the center of the screen. But measured from the center of the screen, this gives us the distance to the mth fringe. And this equation we will use in a number of homework problems that relate to where the fringes are on the screen. So, Young's experiment gives exactly the same kind of physics as we had for the constructive and destructive interference of sound waves. But it had special significance in the history of physics, and therefore we remember it by that name.